In the pre-lecture resources, we have seen that a matrix can be presented as an array of elements, and each element has a position such that we have element ij, and then the dimension of the matrix is given as ij. That means the number of rows times the number of columns. For example, if I have a matrix that is given as A, B, C, D, E, F, this one is the matrix has, and we have 2 rows and 3 columns. That is why the dimension of this matrix will be dimension 2 by 3. And we call the element II as the diagonal of the matrix. And then we also call the trace, if this is matrix A, the trace of the matrix is just the sum of element of A. We are also able to add, subtract, and multiply matrices. So given a matrix A equal to 1, 2, 3, 4, and a matrix B given as 5, 6, 7, 8, those are 2-dimensional matrices, 2 by 2. We can have A plus B equal to 1, 3, 2, 4 plus 5, 6, 7, 8 equal to elements. You add element by element, 1 plus 5, and this position here with that one. The same we can add this one with this one. And of course, we can also have this position, do those operations if they have the same dimensions, the plus and minus. So for this case, that will be 1 plus 5, 2 plus 6, 3 plus 7, 4 plus 8, and we have a new matrix that is 6, 8, 10, 12. This is the addition. In the same way, we can do A minus B, and then we just change the sign, the plus sign with a minus sign. And what we have is 1 minus 5, 2 minus 6, 3 minus 7, 4 minus 8, and then our new matrix will be minus 4, minus 4, minus 4, minus 4. This is how you can do, you can add and also and subtract matrices. And we're gonna see later on when we do, we can also multiply. So we can see in the next slide, we can also multiply 2 matrices. So we can multiply a matrix by a scalar. So consider a matrix A. If we say now 5 times A, that is equal to 5 times our matrix, 1, 2, 3, 4. And then in this case, we multiply each element by 5. 5 times 1, 5 times 2, and 5 times 4. Our new matrix 5A is equal to 5, 15, 10, 20. So in this case, we are multiplying all the elements of the matrix by the scalar. And for each matrix, we also define the transpose matrix noted as A with subscript T. In other notation is also A prime. And MATLAB uses the notation prime to find the transpose of the matrix. So the transpose of the matrix is a new matrix where the rows of the original matrix become the columns and the columns become the rows. So for our matrix A equal to 1, 2, 3, 4, we redefine AT as we have the row, sorry, the column 1, and then we have column 2, and this will become row 1 and row 2. So the transpose would be 1, 2, 3, 4 as our new matrix. And this finds applications in many areas, especially when we have to multiply between two matrices. So how do we multiply then a matrix by a matrix? If we consider our original matrix A, that was 1, 2, 3, 4, and then B, that was, let's say, 2, 1, 4, 3. You can only multiply two matrices if the number of rows of A is equal to the number of columns of B, or the number of columns of B must be equal to the number of rows of A. This is because when you check the product of A and B, there's not a formula how to do it, but I'm going to show you the simplest way to compute A multiplied by B, so you don't need to remember the formula. What is given is that you take the first row of A, and then you multiply and add together with the first column of B. That is why the number of rows of A should be equal to the number of rows of B. Otherwise, the operation won't work. In this condition, you don't need both metrics to have the same dimensions. You just need the number of columns of B being equal to the number of rows of A. So what we do is A times B is actually the sum of the rows multiplied by the columns of B. And what we get in the first here, when we take the first row times the first column, we get the position of the first element, which will be 1 times 2 plus 3 times 1. So this sum sign is what we have here. So we take the multiplication of each element and then we add together. Then the second term will then be the same here, then multiply by the second column. Let's multiply and sum. So what we have in the second column, in the second position, we have 1 times 4 plus 3 times 3. And of course, this one now multiply with the same columns. Then we have 2 times 2 plus 4 times 1, 2 times 4 plus 4 times 3. So our new matrix, which is the product of A and B, will then be given as 5. So 2 plus 3, 5, 4 plus 6, so 4 plus 9, sorry, 13, 2 plus 4, 4 plus 4, 8, 20. This is the product of A and B. And we also define what we call identity matrix. This is the matrix where it's given as 1, 0, 0, 1 for 2-dimensional, and then we can expand it for 3 dimensions. I will just show you quickly how we can do this one in MATLAB. So what we have here, I've already done my matrix A and my matrix B. If you want to find the transpose of A, say A prime, then you get 1, 2, 4, and to do A times B, which should give us a matrix 5, 13, 8, 20. There is a concept of echelon form of matrices. That means if you can reduce the matrix to a form that contains independent vectors. So we say that a matrix is in a row echelon form when it satisfies the following conditions. The first non-zero element in each row, I have also uploaded a PDF file on Kit with a step-by-step guide on how to do basic elementary operations and how to do echelon form. But here I will take an example. When the first non-zero element in each row called the leading entry is equal to 1, each leading entry in a column to the right of the leading entry in the previous row, rows with all zeros elements, if any, are below rows having a non-zero element. What does it mean actually? We have a vector A ref given here, and B and C that are supposed to be in row echelon form. If we look at the condition here, the first non-zero element in each row, the leading entry is 1. If we look at them, that is 1, the second row, 1, the third row, 1. So this condition is satisfied. The same for the others. 1 is the first non-zero element. The second one, each leading entry is in a column to the right of the leading entry in the previous row. This is the first row. We note that 1 is the leading entry. This is the second row. The leading entry is to the right of the leading entry of the previous row. So we are to the right. And then rows with all zeros element, if any, are below rows having a non-zero element. In this case, we also satisfied that this one is to the right of the previous row. The same goes here, to the right, to the right, to the right, here. And we also see that if there is any zero, a row with all zeros, and this row is below all other rows with non-zero elements. This concept of row echelon form are used to look at the rank of matrices, and as well as you can use this technique to reduce your matrix and use it directly when you are solving problem with simultaneous equations. That's what we're going to see later during the lecture today. You can choose, there are different techniques, but if you are able to reduce your matrix in echelon form, then it makes the calculation much easier. For example, in this case here, when you multiply this matrix, let's assume we have a x, y, and z, then you can easily, if we get this matrix and then multiply with x, 1, 2, 3 equal to 1, then if you have the matrix in echelon form, you can easily get the value of x3 and then get x2 and x1. So in solving linear equations, simultaneous linear equations, this technique is very handy. So let's now take an example. There's also another form called the reduced row echelon form. In this case, you only add one more condition at the leading entry in each row. So we have to satisfy all the first three conditions, and then the leading entry in each row is the only non-zero entry in each column. That means this leading entry here should be the only non-zero element. It's mainly for this row here, where we see the lead entry is 1, and within that column it should be the only non-zero element. The same is for this one here, with a single lead entry, and this also should be the only non-zero element. Let's take an example now. So we have a matrix A, and can we transform it into a row echelon form and to a reduced echelon form? So this example is also in the PDF on Kit, and in the PDF I've written using the text what steps to take, and let's now try to see if we can use those steps here to reduce this matrix A into a row echelon form. So we have A 0, 1, 2, 1, 2, 1, 2, 7, 8. So the first one, we see that the first row has a leading entry that is 0. What we want is the first row to have a leading entry that is non-zero. And we do a swap between row 1 and row 2, between this one and that one. So we have an intermediate matrix 2, 1, 0, 1, 2, 2, 7, 8. So then we see that we have a leading entry 1, and we are interested in making the last row also in a form that would give us a leading entry that is to the right of the previous. So what we want first, can we eliminate this component here? To do so, can we multiply the first row by -2 and then add it to the last row? If we do so, what we get in the next step is 1 times -2. So the first one is kept the same. But the last row, because we are transforming the last row such that we multiply the first row by -2 and add it to the last row, we will have 2 minus 2. And then 2 times -2 plus 7. We have 7 minus 4. And then 1 times -2 plus 8. We have 8 minus 2. That will be the step. That's giving us a new matrix 1, 2, 1, 0, 1, 2, 0, 3, and 6. What we can do here, we can multiply, we can remove this one by multiplying the second row by -3 and add it to the third row. The result, if you follow in the PDF, you will see the same steps, is 1, 2, 1, 0, 1, 2, and the last one will be 0 plus 0, and 3 minus 3, and then what we have is also 6 minus 6, and our matrix can be written in row echelon form as 1, 2, 1, 0, 1, 2, 0, 0. So this is the row echelon. If we want to go for the reduced echelon form, that means the leading entry 1 here of the second row should be the only non-zero element of that column. We can multiply the second row by -2 and then add to the first row. What you will get will be 0, 0, 0 kept the same, 0, 1, 2, but the first row will become 1 minus 0, and 2 minus 2, and then 1 minus 4, and that will give us now 1, 0, minus 3, 0, 1, 2, 0, 0, 0, which is the reduced form. And this is just the row echelon form. So some useful properties are independent versus dependent vectors. And per definition, one vector is dependent on other vectors if it is a linear combination of the other vectors. As given here, if you have a vector A, and then you can write it as 2b plus 3c, that means the A can be written as a linear combination of B and C, and thus those vectors are dependent. So we talk about linear dependence of vectors. If we consider the vectors below, A, B, C up to F, note that vector A and B are linearly independent because there is no way you can write A and B as a scalar multiplied by the other. 3 up to 6 will be 2 times, but 2 up to 5 will be 2.5 times. Vectors A and D can be said to be linearly dependent because D is a scalar multiplier of A. So we can actually write D as 2 times the vector A. And that's why we say they are linearly dependent. So that's just the mimic between those concepts. And vector C is a linear combination of vectors A and B. And therefore, the set of vectors A, B, and C are linearly dependent. And vector D, E, and F are linearly independent, since no vector in the set can be derived as a scalar multiplier or a linear combination of any other vectors. So those concepts of linear independence are used to calculate the rank of a matrix, which is defined just as the maximum number of linearly independent column vectors in the matrix, or the maximum number of linearly independent row vectors in the matrix. And both definitions are equivalent. So for a R times C matrix, if R is less than C, then the maximum rank of the matrix will be R. The way around, if R is greater than C, then the maximum rank of the matrix will be C. So how do we find the rank of a matrix? So we can find the maximum number of linearly independent vectors in a matrix, which is equal to the number of non-zero rows in its row echelon matrix. Therefore, to find the rank of a matrix, we simply transform the matrix to its row echelon form and count the number of non-zero rows. If we go back to our previous, what we see is that we have 1 0 row. So we are talking about our row echelon form here. So we have 1 row which is 0, and then 2 non-zero rows. That means the rank of this matrix is 2, also meaning that the matrix has 2 vectors that are linearly independent. let's discuss the notion of determinants. In plain language, if we want to define what the determinant is, a factor or the main determinant of success, we will say it's a factor which decisively affects the nature or outcome of something. So the same with the matrix concept. When we talk about determinant, geometrically it's actually as the volume scaling factor of the linear transformation described by a matrix. And we will see that later on when we watch the video about the linear transformations using matrices. There are different ways you can denote the determinant of a matrix. You can use the absolute value sign, where it says the determinant of A given as a modulus, or in many other books, we say determinant of A, or sometimes just that of A. The determinant of a matrix, which is a scaling factor of the linear transformation, the concept is closely related to that of square matrices and is crucial to the solution of linear equations. So we're going to see later on how this one affects the solutions of linear equations. So given a square matrix A, 2 times 2, or 3 times 3, the determinant of A can be computed as A11 times A22 minus A12 times 21. Basically, what is going on is that you multiply this way minus multiplication this way. So if you have A11, A21, A12, A22, the determinant is multiplication minus multiplication this way. So instead of remembering the formula, if you remember how to multiply this way minus multiplication the other way, then what you get is what is given here. For a 3 by 3 matrix, the determinant is computed as given here. The easiest way to remember is to use minus. We learned this technique last time. If we want to find the first element, we will have plus, minus, plus, plus, minus, plus. So we take A11 here, and then we do the multiplication by keeping this one away, and then do the multiplication here, which is given here. So what we have computed in this matrix of 2 by 2 is then down here, multiplied by the leading A11. So this is how to remember the computation of determinant instead of remembering all the formula, which is quite difficult. And then the second term, which is a minus, we then take this A12. Let's assume now that we hide this one and this one. What we are dealing with now is this 4 element here. Which is given in blue as this one. And so on as a quite straightforward to compute the determinant. In general, the formula is given here. You get the first element with the sign, and then you multiply with the minor, and the minor is given as the determinant of the 2 by 2 matrix. If we go back to our matrix A, 1, 3, 2, 4, and want to find determinant A, that will be 1 times 4 minus 2 times 3, which is 1 times 4 minus 2 times 3. In this case, we have minus 2. And MATLAB also gives us a way to compute determinant. Det of A. MATLAB is the determinant of our matrix A. This is minus 2. So we can also find the inverse of a matrix. Given a square matrix n times n, the inverse of A is another n by n matrix, given as A in the power of minus 1, such that multiplying the matrix with its inverse is equal to the identity matrix. This example that the inverse is given, and then if you multiply by A, what you get is a identity matrix with 1 as leading element in each row. So there are two ways to determine if the inverse of a matrix does exist. You can determine the rank of the matrix. The rank of a matrix is a unique number associated with a square matrix. If the rank of n by n matrix is less than n, the inverse does not exist, or the matrix doesn't have an inverse. Many uses the determinant as the deciding factor. When the determinant of a square matrix is equal to 0, the inverse for that matrix does not exist. Also because it is quite easy to compute the inverse of a diagonal matrix, where you only have non-zero in the diagonal, which will just be the reciprocal of each element. Or for any other matrix, let's say the 2 times 2 matrix, the inverse is actually scaled by the determinant. That is why if A equal to 0, then the inverse does not exist. For a 2 by 2 matrix, it's easy. You just compute the determinant and then take your original matrix, swap between A and D, and then change the sign of minus of B and C to get the inverse matrix. In our case, our A was 1, 3, 2, 4, and we've computed the determinant as minus 2. To get the inverse of A minus 1, what we do, we take 1 over the determinant, and then we swap between A and D. So 4 becomes here, and 1 come here. And then we change the sign of our C and B. Our matrix will then be 2, so minus 2, 3 half, minus, so plus 1, and minus 1 half. In MATLAB as well, you can just say A in the power of -1, which will give you the inverse of the matrix. And I believe there is also a command called INV, yeah, which does the same as taking the power of the matrix in -1. So let's have a look at matrix applications. How do we use those concepts in engineering? And why do we need to know how to manipulate matrices? One of the area where we can apply matrices is the solution of simultaneous linear equations. And the problem of simultaneous linear equations is usually given as a set of equations with multiple unknowns. In this case, x1 up to xn are the unknowns, and we know the coefficient of those unknowns. This can be represented as in a matrix form as a matrix times a vector that equal to a vector. If we represent our matrix with A's, and then we have our x up to xn, this will be equal to y1 up to yn, just to express it in a matrix form. So we're taking a matrix times a vector equal to a vector. How do we do that? So to solve n linear equations in n unknowns using matrix method, we first express it in the matrix form ax star equal to y. We pre-multiply both sides by the inverse of A. So what we do is taking A minus 1 times AX equal to A minus 1 times A. So multiplying an element in both sides of the equation doesn't change anything. And we know that minus A times A is equal to the identity matrix. And then we can express S as A minus 1y. So to solve this equation, what you need to do is just to find the inverse of the matrix and multiply it by y to get x. Let's take an example here. We have 3 equations with 3 unknowns. If we take our A as the coefficient of x, we have in the first line 1, 2, 2, 2, 2, 2, 2, 2, 1 times x1, x2, x3 equal to 1, 2, 3. If we are using normal algebra, what we will do, we will try to get rid of x1 in those 2 equations by multiplying by 1 and adding, and so on. But in this case now, we set it up in a matrix form. Our solution is basically just x1, x2, x3 will be equal to 1, 2, 2, 2, 2, 2, 2, 2, 1, minus 1 times 1, 2, 3. So if you multiply the inverse by the vector, we get the solution of the equation. And if you have MATLAB, this is very easy to do. So in MATLAB, the matrix R, if I take the inverse of R, that will be minus 1, 1, 0, 1 minus 1.5, 1, and so on. We go back to the slide. so that we have the solution x1, x2, x3 equal to the inverse minus 1, 1, 0, minus 1.51, 0, 1, minus 1, and this should be times 1, 2, 3. And what we get is the matrix 1, 1, minus 1, which is the solution of the simultaneous equations we had here. Another application of matrices is the variance-covariance matrix. I'm going to play a video for you that I found on YouTube that explains the concept of variance and covariance matrix.